A square wave is a non-sinusoidal periodic waveform, in which the amplitude alternates at a steady frequency between fixed minimum and maximum values with the same duration at minimum and maximum. The transition between minimum to maximum is instantaneous for an ideal square wave. This is not realizable in physical systems. Square waves are often encountered in electronics and signal processing. Its stochastic counterpart is a two-state trajectory. A similar but not necessarily symmetrical wave, with arbitrary durations at minimum and maximum, is called a pulse wave. Origin and uses. Square waves are universally encountered in digital switching circuits and are naturally generated by binary logic devices. They are used as timing references or clock signals. Because their fast transitions are suitable for triggering synchronous logic circuits at precisely determined intervals. However, as the frequency domain graph shows, square waves contain a wide range of harmonics. These can generate electromagnetic radiation or pulses of current that interfere with other nearby circuits, causing noise or errors. To avoid this problem in very sensitive circuits such as precision analog to digital converters, sine waves are used instead of square waves as timing references. In musical terms, they are often described as sounding hollow, and are therefore used as the basis for wind instrument sounds created using subtractive synthesis. Additionally, the distortion effect used on electric guitars clips the outermost regions of the waveform, causing it to increasingly resemble a square wave as more distortion is applied. Simple two-level Rademacher functions are square waves. Examining the square wave, using Fourier expansion with cycle frequency f over time t, we can represent an ideal square wave with an amplitude of 1 as an infinite series of the form. The ideal square wave contains only components of odd integer harmonic frequencies f. Sawtooth waves and real-world signals contain all integer harmonics. A curiosity of the convergence of the Fourier series representation of the square wave is the Gibbs phenomenon. Ringing artifacts in non-ideal square waves can be shown to be related to this phenomenon. The Gibbs phenomenon can be prevented by the use of sigma approximation, which uses the Lanczos sigma factors to help the sequence converge more smoothly. An ideal mathematical square wave changes between the high and the low state instantaneously, and without under or overshooting. This is impossible to achieve in physical systems, as it would require infinite bandwidth. Square waves in physical systems have only finite bandwidth, and often exhibit ringing effects similar to those of the Gibbs phenomenon, or ripple effects similar to those of the sigma approximation. For a reasonable approximation to the square wave shape, at least the fundamental and third harmonic need to be present, with the fifth harmonic being desirable. These bandwidth requirements are important in digital electronics, where finite bandwidth analog approximations to square wave-like waveforms are used. The ratio of the high period to the total period of any rectangular wave is called the duty cycle. A true square wave has a 50% duty cycle, equal high and low periods. The average level of a rectangular wave is also given by the duty cycle. So by varying the on and off periods and then averaging, it is possible to represent any value between the two limiting levels. This is the basis of pulse width modulation. Characteristics of imperfect square waves. As already mentioned, an ideal square wave has instantaneous transitions between the high and low levels. In practice, this is never achieved because of physical limitations of the system that generates the waveform. The times taken for the signal to rise from the low level to the high level and back again are called the rise time and the fall time respectively. If the system is overdamped, then the waveform may never actually reach the theoretical high and low levels, and if the system is underdamped, it will oscillate about the high and low levels before settling down. In these cases, the rise and fall times are measured between specified intermediate levels, such as 5% and 95%, or 10% and 90%. The bandwidth of a system is related to the transition times of the waveform. There are formulas allowing one to be determined approximately from the other definitions. The square wave in mathematics has many definitions, which are equivalent except at the discontinuities. It can be defined as simply the sine function of a periodic function, an example being a sinusoid, which will be 1 when the sinusoid is positive, -1 when the sinusoid is negative, and 0 at the discontinuities. Any periodic function can substitute the sinusoid in this definition. A square wave can also be defined with respect to the Heaviside step function U or the rectangular function. T is 2 for a 50% duty cycle. It can also be defined in a piecewise way, when in terms of sine and cosecant with period p and amplitude A. A square wave can also be generated using the floor function in the following two ways: directly and indirectly, where m is the magnitude and u is the frequency.